Yeah, we had seen the applications of Archimedes principle and buoyancy. So let's continue from that point onwards today. So let's revise the concept of the statement of Archimedes principle and then look at few examples of application. So the statement of Archimedes principle is that the upthrust or buoyant force equals to the weight of fluid displaced. So mathematically, this becomes density of the fluid into volume of the submerged part into G. And in case the object is completely submerged, the volume of the submerged part becomes the total volume. So this, along with its applications, are what we have discussed last time. So let's look at an example question. Now we have a rubber spherical shell which has an inner radius of 2 centimeters and outer radius of 3 centimeters. Okay. Floats in water with half of it submerged. Okay. So if you look at the cross section, if you cut the sphere into 2 equals halves and you look at the cross section, so you realize that it's not a solid sphere, it's a shell. So this is what the cross section looks like. So this inner radius is 2 centimeters and the outer radius, that is 3 centimeters. So now when you place this sphere, now from outside it looks like a sphere only. You can't tell that it's hollow from inside. But when you place this in water, it floats such that 50% of it is submerged. Density of water is 1 gram per cc. So from this we have to find the buoyant force acting on it. Take G as 10 meters per second square for that. And secondly, we have to find the density of rubber. So just try out this question, people. There's an application of the principle of flotation.
Sir,
Yes. Yes, what happened?
sir, we have to note down the upper part here.
No, you don't have to note down. If you go through your notes previously, you've written this down. Okay. Just try out this question.
Okay, sir.
Okay, so let's work out this question quickly, people. So it's pretty straightforward. What you have to understand is that the weight of the object is balanced by buoyant force. So buoyant force here will be density of water into volume of submerged part into G, whereas the weight will be density of rubber into volume of rubber into G. Now from this diagram, you will understand that the volume of rubber is basically what it is, 4 by 3 pi into 3 centimeter cube minus 2 centimeter cube. Because it's a shell, no? Whereas the volume of submerged part is 50% of 4 by 3 pi into 3 centimeter cube. Okay. So the buoyant force, which is equal to the weight, is equal to density of water, which is 1 gram per cc, multiplied by 2 by 3 pi into 27 in cubic centimeters into G. So it is how much now? 18 pi grams into 10 meters per second square. So it is 18 pi by 1000 to 10. So that is 9 pi by 50. Newtons. That is the buoyant force. There is a buoyant force. Okay. Now similarly, now we'll use the fact that mg, which is equal to the buoyant force, is density of rubber into 4 by 3 pi into 27 minus 8 g. That should be equal to this. So from this you will get that density of rubber is equal to density of water into this thing 4 cube, sorry 2 cube outer radius cube, that is 3 centimeter cube by 2 of 3 centimeter cube minus 2 centimeter cube. So is this kind of a factor? So just make a note of this. See, when you are considering the volume of the submerged part, how much water has been displaced. So how the inner radius is going to come into play. You're understanding, Krish and Yash? As 50% of the sphere is inside water, how much water has got displaced? वो outer volume का 50% है ना? Water is not going to get inside, na? Understood now? No? Krish, it's clear? Okay, good, good. So that was the trick in this question. No? We can't blindly just apply the formula.
Excuse me, sir. Sir, I did not get the second step that you wrote in.
Which one, beta? The buoyancy one or the weight
Yes,
one?
sir. Buoyancy one, second step.
Okay. So the buoyancy ka value kitna hai? It is in that the volume submerged is what 50% of the outer volume, na? Because the ball is inside water, na? Half of it is inside water. So how much is the volume submerged and therefore displacing the water? It's 50% of 4/3 pi of outer radius cube.
Yes, sir.
No, so that's why this term is this much. So now how much is the buoyant force exactly? It is equal to the density of water. Okay, this is density of water. This is the submerged volume into G. Got it, no?
Yes, sir.
Whereas when it comes to the weight of the object, this will not be 4/3 pi 3 centimeter cube. This will be 3 centimeter cube minus 2 centimeter cube because the rubber is only present in the shell. Na? It's not inside. There's no rubber inside. So
Sir,
this is the volume.
My doubt was how did we get it as 8 pi grams into 10 meter per second square? That was.
अच्छा, so I've just ग्राम पर सीसी को सीसी से मल्टीप्लाई किया तो ग्राम में मिल गया ना.
अच्छा, okay.
So I've kept it in CGS unit instead of converting it. That's all. Later I've converted to newtons by dividing by 1000. Yes, Krish, that's correct. This will come out to be approximately 0.7. In fact, we'll go up to second place of decimal 0.7. Okay. So anyhow, hope the method of the question is clear. So you will find a lot of questions like this as part of H.C. Verma's bank of questions of hydrostatics. First 22 questions of fluid mechanics, which I told you to work out. Okay. Then the rest of the questions will be fluid dynamics, hydrodynamics, which we are going to discuss today. So after today's lecture, you will be mostly be able to attempt questions from H.C. Verma fully. And next lecture, we can look at solving the doubts and questions and all. Anyhow, so let's move forward. Now, next thing we will look at is pressure gradient. Going back to the concept of pressure gradient, but in a fluid at rest in an accelerated vessel. So going back to Newton's laws of motion, an accelerated vessel becomes a non-inertial frame. So the first case we will see where we are in a vertically accelerated. tank or vessel, whatever. So let's say we got an open vessel like before with any ideal fluid inside it. But this time, the whole vessel with the fluid is vertically accelerated with acceleration A, let's say. So what's going to happen now is that if we consider the free body diagram of a volume element of fluid like this, okay, over here, this volume element. If we consider its free body diagram, but in the non-inertial frame of the tank, which is having a vertical acceleration A. So in this frame, it is at rest. So in this frame, the forces acting on it are pseudo force, its mass is delta m, okay, weight, and then the forces because of pressure, which we had seen earlier. The lower surface will experience pressure into area, the upper surface will experience some change in pressure into area, okay, because we are considering this as the y coordinate and this as delta y, this surface area is A. So now when we consider the equilibrium, we'll see P plus delta P plus delta M into G plus E. This will be balanced by P into A. So our delta P will come out to be minus of delta M into area. Yeah. So there'll be a delta P will come with a minus sign. But also this term will be G plus E. Now the mass of that element is density into volume. So that's density into area into the thickness delta Y. So we write that, we can see that delta P so our vertical pressure gradient's value has changed. Because of the pseudo force acting. It has changed from only rho G to rho of G plus A. So this is our vertical gradient. Okay. And our horizontal gradient will still be zero. We don't need to make another FBT to prove that. So this happens when our tank is vertically accelerated. So just make a note of this, we will discuss. Okay, people. So hope this is clear.
Sir, can you explain it again?
So free body diagram, pseudo force. You remember from Newton's laws of motion. It acts opposite to the acceleration of the reference frame. Okay. So pseudo force is acting downwards. Gravity acts downwards, and the difference of pressure into area balances this. So hence we get delta P as a negative quantity. Pressure decreases as you're going up in the vertical direction. It's very similar to the derivation of pressure gradient we had done in the first lecture of hydrostatics. The only addition is the pseudo force because we are now in a non-inertial frame. Okay, is this clear now?
Yes, sir. Sir, just a second.
Okay.
Done, sir.
Then now the second situation we'll see in which this concept of pressure gradient changing because of the acceleration of the vessel in which the liquid is there is when we have a horizontally accelerated reference frame. So now imagine a situation where we have liquid in a tank which is accelerating along the horizontal direction like this. So what you will understand intuitively is that the surface of the liquid will no longer be horizontal, because now pseudo force is pushing the liquid backwards opposite to the acceleration, whereas gravity is pulling it down. So that combination of forces acting on the liquid will cause the surface to be inclined. And as a result of that inclination, there is going to be, or as a result of pseudo force, actually, we can say there is going to be, in addition to the vertical pressure gradient, there's going to be the horizontal pressure gradient. Okay. So now we will consider two types of volume elements. One which we'll place like this at a distance x like this. Its own thickness is delta x. So we'll consider this volume element, and we'll consider only the just a minute. Trying to get back to the screen. Yeah, so yes, so I'm coming to that part of the question only. So now if we consider this volume element, which is at a distance x from this side, but also whose own thickness is delta x. Okay, and this side has an area of A. So when I consider this volume element of volume A into delta x, so when I consider its free body diagram, and in the FBD I consider only the horizontal forces acting on. So FBD of the volume element in the non-inertial frame, okay, and only showing horizontal forces. We'll take care of the vertical forces also, but that we'll do in a separate diagram. So in this non-inertial frame of the tank, which is accelerated like this, so this will experience a pseudo force in this direction. And that will have to be compensated for by a pressure difference now. And this is at rest in this frame. So we can see P is the pressure at x equal to x. P plus delta P is the pressure at x equal to x plus delta x. So now considering the equilibrium of this, we can see P into A has to balance P plus delta P into A plus this pseudo force. So again, we see that there is a negative pressure difference. Delta P comes out to be minus delta M by capital A to small a. And of course, we'll substitute so from this we will get that delta P is minus rho A into delta X, or in addition to the vertical pressure gradient, now there is also a horizontal pressure gradient. such that the pressure is decreasing uniformly along the positive x-axis, because pseudo force actually acts along the negative x-axis. So pressure decreases along the positive x-axis, whereas gravity similarly acts along the negative y-axis. So it creates a negative y gradient of pressure, which will be same as before. So this is now showing that we have a uniform horizontal pressure gradient. And that is happening due to the horizontal pseudo force this time. Whereas delta P by delta Y, that will remain minus rho G. There will still be this uniform vertical pressure gradient because of gravity. So to understand how this one comes, now you just try this yourself. You take a volume element like this one and make the FPD of that and show only vertical forces on that volume element. And you should be able to show that. It should be a very comfortable derivation that you have this kind of vertical pressure gradient. So there's a combination of horizontal and vertical pressure gradient now. As you go vertically upwards, your pressure is decreasing. As you horizontally move along the x-axis, the direction of the acceleration, that way also the pressure decreases. Okay. So what that results in and why the surface is inclined, we'll discuss in a bit. First, note this down. So this is not a question of slow or fast. Okay, whatever the value of acceleration is, the more the acceleration is, more inclined the surface will become. Okay, but the liquid is at rest with respect to the tank, so it's at rest in a non-inertial frame. Doesn't matter whether the tank is accelerating fast or comparatively slow. The situation will be the same. It will only affect the value of the pressure gradient. The faster the tank is accelerating, the larger the value of the pressure gradient. Okay, so hope this part is clear. So the free body diagram of this other volume element will also look very similar to what we have done before. So since we are considering only the vertical forces on this, horizontal forces we have taken care of in that free body diagram, vertical forces in this one. So here P is pressure at Y and P plus delta P is the pressure at Y plus delta Y. So by balancing the forces and all that, we get this other relation. So once we have understood this,
So
coming
just a
back to
bit. Done, sir.
so once we have understood this pressure gradient, we can not only understand the reason behind the surface being inclined, but we can calculate the angle of inclination also. So this is accelerated at A. Now let's say the tank has this length is L over here, and the height of water on this side is H1. The height of water on this side is H2 as a result of the horizontal pressure gradient that's developing, such that the surface is having an inclination of theta with respect to the horizontal. This angle is theta. Okay. So now what we can do is we can first of all consider 2 points right on the surface of the liquid over here and here. So we can see that pressure at the point A is equal to pressure at the point B, which is equal to atmospheric pressure. Then right below A, we can consider a point, let's say C, and right below B, we can consider a point, let's say D. So pressure at C will be equal to PA plus rho G H2. Okay, because here we have considered the fact that vertical pressure gradient is minus rho G. So pressure at A minus pressure at C upon the vertical displacement H2 is equal to minus rho G. So from this result, we would have got this. Okay, and similarly, pressure at D will be equal to pressure at B plus rho G H1. Because again, consider this. From this, we got this. Okay. So now substituting this information here, these two become like this, that pressure at C is atmospheric pressure plus rho G H2. Pressure at D is equal to atmospheric pressure again plus rho G H1. So if we subtract these two, you can see that this pressure difference is equal to this quantity. Now also comparing C and D and using the fact that delta P by delta X was minus rho A. So pressure at D minus pressure at C divided by the horizontal delta X between them, which is L, should be equal to minus rho A. So from this, we will get that this pressure difference is rho A into L. So now compare this equation and this equation. So this equation is basically coming from by using vertical pressure gradients. Whereas this one here was coming by using horizontal pressure gradients. But comparing the two of them now, we can see
Sir,
that PC minus PD so H2 minus H1 by L is A by G, and that is tan theta. So we have this formula now that tan theta is equal to A by G. It's a very easy formula to remember that tan theta is equal to A by G, and this is the derivation of it. Okay, so now let's move on to an application example, this kind of concept. So again, very common question at JEE kind of exam. So you have this U-tube, which is initially stationary. But initially it is stationary with water filled up to a certain height. Now, next situation, what we are doing is we are accelerating it. So as a result of that, the water level changes like this. So whatever this original level, compared to that, one side level goes up, the other side the level comes down. So if this height was h0 and this length was L, now this new height is h1, this height is h2. So here the tank is at rest, or the U-tube is at rest. Okay. This is water. So given that initially this height h0 on both the sides, when the U-tube was at rest, this height h0 was 20 centimeters, and the length of the tube, the horizontal part's length, is 60 centimeters. Okay. And the acceleration E that we have given it is 2.5 meters per second square. Take G's value as 10 meters per second square. We want to find h1 and h2. So just try out this question. Assume that the tube is uniformly thick, its cross-sectional area is uniform everywhere, and the radius of that cross-section is quite small in comparison to the length L and h1, h2, etc. Yeah, they had asked you to leave out the question involving simple harmonic motion, because we'll be discussing that in the chapter on oscillations, which will come a little bit later. After fluids, we'll be doing properties of matter, and then we'll come to oscillations. So that question in H.C. Verma, which has a spring attached to a block and then it's made to oscillate when partially submerged in water, just leave out that question for now. And mark in the book that we'll discuss it during harmonic motion chapter. Yes, very good, Tantresh, that's correct. So what we can see here is that if we compare these 2 points, okay, let's say A and B, and we take this as our x-axis and this is our y-axis. So in this situation, in this second situation, our vertical pressure gradient is minus rho g, okay, and our horizontal pressure gradient is minus rho e. So this will tell us, for example, that pressure at the point A should be equal to atmospheric pressure plus rho g h1, and pressure at the point B should be equal to atmospheric pressure plus rho g h2. This information will come from vertical pressure gradient, and from this we can see that this pressure difference should be equal to this much. Okay. But from this we will also get directly that pressure at the point A will be equal to pressure at the point B plus rho AL. We'll also get that the same pressure difference is equal to rho AL. So now connecting these two equations, okay, so from equation 1 and 2, basically get that same tan theta kind of equation, that rho AL is equal to rho G H1 minus H2. So from this we'll get that H1 minus H2 is equal to A by G times L. So when we substitute the values here, we'll get one relation, that H1 minus H2 is equal to A by G ratio is 1 by 4 and L is 60. So it will come out to be 15 centimeters. So the difference in the heights is 15 centimeters. Now also there will be conservation of volume. So between diagram 1 and diagram 2, total volume of water is conserved. So in diagram 1, the volume is equal to 2h0 plus some length plus L, that is, okay, into some kind of cross sectional area. In the second diagram, the volume is H1 plus L plus H2 times the same area. So conserving the volume, you can see that 2h0 is equal to H1 plus H2. So H1 plus H2's value should be equal to 2 times H or 2 times H0. So that should be 40 centimeters. So now you solve these two equations together and your H1 will come out to be 27.5 centimeters and H2 will come out to be 12.5 centimeters. So we are using a combination of concept of pressure gradient and one very simple logical idea that volume of liquid is remaining conserved. So this is a typical example of a numerical problem with application of horizontal pressure gradient because of horizontal pseudo force or horizontally accelerated frame. So very important type of question. Okay. Please make sure that you understand the solution properly before we move on. Okay, so yes, hope you understood how the values are coming to this. Tantrish, you got the question correct. I think yes, you have made a mistake of some factor of half somewhere. So might be a numerical mistake you made. Okay, people. So hope this question is clear. Now, from this, we move on from hydrostatics to the second part of fluid mechanics, hydrodynamics. So in hydrodynamics, we will be studying a type of fluid motion which is called streamline motion or steady flow. Of an ideal fluid. We've already understood the term ideal fluid before. Now let us understand the definition of steady flow or streamline motion. So when a fluid is moving in such a way that if we consider a cross section to the path along which the fluid is moving, then at that cross section, every fluid molecule, or you can say every small volume of fluid, should have identical velocity. So they should move along the fluid elements, they should move along well-defined trajectories or paths, which are called the streamlines. So it's a very ordered kind of motion. So now if we consider some cross section over here, any fluid element going through that cross section will have the same velocity as this one. So steady flow or streamline motion is a highly ordered kind of motion of a fluid such that any volume element moves along a steady and well-defined path or streamline, and volume elements simply follow each other identically along these streamlines, such that at a given cross section, any fluid volume element will pass through with the same identical velocity. So that is a very descriptive sort of way of explaining what is streamline or steady flow. Now, make sure you understand this and write down the keywords here. Now, after this, we'll also understand how we can write mathematical equations based on this descriptive sort of explanation of streamline motion. Yeah, students, sorry, there was a connection issue at my end. So anyhow, let's pick it up. We're discussing about steady flow and streamline motion. So I hope all of you have written down this definition. Oh, many students have logged out. Okay. Okay, so what we'll do then is, because many students have logged out, we will pick up streamline motion again in the next lecture. In the meantime, let's do another practice problem based on hydrostatics. Okay. Okay, so let's say we have a situation like this, that okay, so I'll explain the question. So what is happening is, we have a block which on the outside of it looks like a solid plastic block. Okay, but and we when we wait as normal, uh, yeah. So Diti, I've not, I've also, like, I got disconnected and I've just joined. So this is the question I'm discussing now. Because many students have logged out. So instead of teaching ahead with hydrodynamics, I'm doing a revision question of hydrostatics. So I'm explaining the question again. So there is this solid block, solid plastic block, which when we weigh it in air, it weighs 56 grams. Okay. And the density of plastic is 6 gram per cc. But when we submerge it under water and weigh it again, so as you know, anything underwater will tend to weigh less because of the buoyancy. So it weighs 46 grams only. So there's a difference of 10 grams because of the buoyancy. But also, apparently, the solid plastic block is not completely solid plastic. There are some air cavities inside it. There are some cavities inside it. So we have to investigate whether this theory is correct, that whether or not there are any air cavities. And if it is correct that there are air cavities, then we have to find the fraction of the block's volume which is occupied by the cavities. Like, let's say 10% of its volume is actually cavities and not plastic, then that fraction would be 1 by 10. So like that, we have to calculate the fraction. So just give this a try. Okay. You can think of how forces in a free body diagram would act on this in the two situations, when it is weighed in air and when it is weighed underwater. Just assume it's weighed using a spring balance or something like that, suspended from a spring balance. So the tension in the spring is what is balancing the weight when it's balanced in air, whereas it's balancing the apparent weight when it is balanced underwater. Okay. And that tension is what we read as the weight. Okay. So it's not necessarily the true weight, as you know. Okay, people, so let's just understand the situation. So let's say this is my plastic block, and initially I've used a spring balance. So I'm able to measure the so-called weight from the spring force. So let's say it's kx0 is equal to mg, and this is equal to the true weight. So it's 56 grams into acceleration due to gravity. So this is my first equation. Okay. But now I place this whole system inside water. Maybe not the whole system, at least the plastic block is completely submerged. The spring may or may not be inside water, it doesn't really matter. So now what is happening is that the reading of the spring or the extension of the spring will change because there is the additional force of buoyancy that the water is applying. So in this situation, what is happening is Kx is balancing mg minus buoyant force. And this is given to us as how much? This is given to us as, where is it now? 46 grams, right? This. Now again, we have to understand the logic of this. So this is going to be density of plastic into volume of plastic into G. This is like that problem we did earlier. Whereas buoyancy is going to be density of water into volume of the block, the total volume of the block. Why? Because the total volume of the block will be the actual volume of plastic plus the volume of cavities. Okay, so imagine inside it's got some cavities which we can't see from outside. So the actual volume of plastic is only this, is minus the volume of the cavities. Okay, so this is equal to 46 G, taking in CGS unit, and compare this with this. So actually, if you first of all just subtract the two equations, equation 1 minus 2 will show you that buoyant force is equal to 10 grams into G. So that is showing me that density of water into volume of the block is equal to 10 grams. So that means the actual volume of the block is how much? The volume of the block is 10 cubic centimeters, because density of water is 1 gram per cc. Okay, now this is also showing me from the equation 1 that mg is equal to 56 grams into G, or m is equal to 56 grams. So density of plastic into the true volume of plastic is 56 grams. So what is the volume of plastic accordingly? It is 56 divided by 6, which is how much now? 28 by 3, right? So that is 9 point something, 9.33, right? 9.33 cubic centimeters. Okay. So you can see there's a difference, a small difference, but it's significant. So you can see that the volume of the cavities is the volume of the block minus the actual amount of plastic in volume which is present. So that is about 0.67 cc. So the fraction of the total volume of the block, which is the volume of the cavities, is this. .067, or you can say it is 6.7%. It's a very small fraction, but it is there. So 6.7% of plastic is actually missing inside. What we are seeing from the volume outside is not the true volume of plastic, because there are cavities inside. So this was an effective method used by metallurgists earlier on, before the age of various other detection techniques, including spectrometry and all that. just to measure the purity by density of metallic objects. This could be used. Okay, so anyhow, the population has rapidly declined. So we will conclude today's session here today. And
Sir,
yes,
I have to write last.
yeah, write it down. Okay. So with this, we'll conclude today's lecture, and next time we'll pick up hydrodynamics. It's a small topic, so we should be able to complete the concepts at least in next lecture. We'll also keep aside some time for discussion of questions from hydrostatics from HCV. So whatever stage of completion of those problems you are at, try to finish them before the next lecture so that you can discuss your doubts with me. Or at least while I'm discussing others' doubts, you can understand what's happening. You're familiar with the questions. So that's it for today's session, people. Wish you all the best.
Bye, sir. Thank you, sir.
Bye, sir. Bye, sir. Thank you, sir.
Yeah, bye, people.